All right, well, welcome everybody to week 3 of Introduction to Astronomy Research 2021. We're happy to have you all here today. And on today's agenda, we'll be discussing NASA's Exoplanet Archive, ESO's Gaia spacecraft, and we'll have a discussion of the TOI-700 Planetary System. Should be a really interesting day. We've spent a few weeks getting up and rolling, and today we really dig into some great topics that are used every day in astronomy research. Just today at my group meeting, someone started the discussion with a screenshot of NASA's Exoplanet Archive showing the distribution of brown dwarfs around M-type stars. And so you're going to learn some stuff today that you'll be able to use right away. It should be really exciting. And without further ado, I'm going to hand it off for our first part of the discussion on let's see, Exoplanet Archive. And so Emily, are you ready to get us started?
Sure thing.
Take it away.
Hello, everybody. Thank you so much for coming in today. I will be going over the basics on how to use the Exoplanet Archive, including how to navigate some of the tools on the website, as well as to navigate specific target pages. So let me go ahead and share my screen. So here's the front page of the NASA Exoplanet Archive. It contains hot links to several news articles, as well as basic statistics about more recent or more prominent missions, as well as some shortcuts to some of the tools that we will be using today. Before we get into the tools, the most useful thing that I know about how to use the NASA Exoplanet Archive is to essentially look into a specific target. So today we are going to be first looking at, let's say, TOI-216. So you can go ahead and put in the name of the star or the name of the planet. The naming jargon is a little different. The normal TOI name usually belongs to the star itself, and then planets will have subsequent lowercase letters, usually B, C, D, E, and so on. These smaller lowercase letters are actually assigned in order that these planets were founded. So TOI 2016.01, or most likely 2116b is another naming for it, was the first planet. TOI 216.02, second planet. So this is a system of a little less than a solar type star. Right here you can see the stellar radius, or the radius in compared to our own star, as well as the temperature. And here we have the comparative radii of these two ones in context of Jupiter radii. So on this page, it is a small, relatively new system. And here you can see the method of which they were found, transits, the year that they were found, as well as their reference papers. These are very important to know and find, especially if you want background on a system that has been observed for a long time across multiple missions. So it links to NASA ADF's website, where you can find the publisher as well as ArcSiv sources for this system. So on every page, you will find the stellar parameters, where it gives you all of the information on the star that we are able to have with the technology that has been subjected on that system. So here we have some Gaia information, some publisher information, and it has a plethora of different values. And then below it, we have information on both the planets. TOI 216.02, you can have everything in terms of transit parameters, as well as periastron, orbital dynamics, approximate equilibrium temperature. This is great if you are specifically doing work where you are combing through one target at a time in order to, okay, my bad.
You're doing great. Carry on.
Sorry. So, especially if you are going through single targets at a time looking for anomalies like I have in previous research, it is great to know these specific parameters when you are looking for anomalies. You can also tell a lot by the possible formation of these systems from the parameters of the planets and the parameters of the star. So here we have TOI 216.02 and then 0.01. And then it links to the associated stellar parameters, which I believe will just take you, well, it should, if you don't have a trackpad, should take you all the way back up here and highlight where exactly these parameters are being linked from. The primary parameters that are being used for this specific page are coming from this publication. Whoops. So this is how you look at a singular system, especially if you are going into the background of it, or if you are looking for specific characteristics of that system, or you need to do a population study. These single pages are great for gathering that type of information, as well as seeing what other people have done to publish about it. To find all publishable materials on a specific target, simply hit bibliography. And here you can find all of the papers that either reference it or reference the system generally. This is especially good if you are writing a paper and you need sources to draw about this specific system or systems like it. So now that you've seen a single system, now it is time to consider, how do I draw information across multiple systems, a lot of systems? You might need to do a population study on systems that were observed in a certain mission. So under data, you will find all of these wonderful links leading you to a bunch of different source pages. And here we're going to go to the basic planetary systems. And this should take us to the confirmed planetary systems table. There we are. This is a very large table, and it consists of all known confirmed planets to date. And it tells you a lot about all of these different systems, when they were found, what the discovery facility was, what method was used to find them, how many planets are in that system. Go ahead all the way over to planetary parameters. To navigate specific statistics of this page, there are these little entry bars here that can help you narrow down some of your options. For example, if you're only interested in transiting planets, you can put in transit as the discovery method, and it will sift out all the ones that were found via transits. And there you go. All of these were found in transits. So what about if you want to find a transiting system or a planet that transits in the year 2009? There we go. And now you've narrowed it down even further. This specific portion, this planetary systems table, will be used in the tutorial later in this module. Yes, and then if you delete whatever is in these, it will reset into the full table. So that is how you use this. In order to download a table, you simply go into download table, where there are multiple ways for you to download it. One of the ways that I specifically have been taught to download is in tab separated or CSV format, and download checked and filtered rows, especially if you are doing a population study. And then from there, you can simply download the table, and it will download directly into your downloads folder of your computer. So that is all great and wonderful, I'm sure, but one of the best ways of using this data is to visualize it. One of the many tools that is used in this NASA Exoplanet archive, as mentioned before, was the Confirmed Planets Plotting tool. And here, you can really sort of play around and understand how certain populations of confirmed exoplanets are essentially influenced by our detection methods. So this is a basic mass and radius relationship graph, pre-generated, but there are all sorts of different there are all sorts of different ways of developing plots. You can do it by number of planets in system, perhaps. That's easy enough to do. All you have to do is choose your axes and redraw them, and they will label them out for you. So 1, 2, 3, 4, 5, and 6 separate numbers of planets and systems. Or you could do it by semi-major axis versus planet mass. And here we have an interesting collection of populations. Here you can see a very small but noticeable separation in these little clumps. This is usually done by observation bias from our instruments that we use, as well as where they are located. Not all planets transit. A transit is actually a very, very rare event that can only occur if we, as well as the system, has their planet pass in between us. So while almost 30,000 confirmed planets is certainly a lot, it is a mere fraction of what we could possibly be observing with the technology that we currently have. But what we have been able to discover, we've been able to find out many amazing things about the structure of planets, of planetary systems, and what's possible. Things like compact systems, where we can have 6 entire stable orbits within the orbital distance of Mercury of our own system. Those exist. Hot Jupiters, Jupiter-sized planets that orbit maybe 10 days or less around their star, stable orbits. And these graphs and this tool is a great way to visualize exactly what we have been able to find so far. So the last tool that I would like to outline with today is the Transit and Ephemeris Service. One of the main forms of research that I did as an undergrad before being accepted into research with Stephen Kane was a follow-up observation of TESS sectors. A sector is about a month long, and it is a portion of the sky. And TESS especially focuses on really bright nearby star hosts. So I would comb through all of these different light curves individually. And when I see something that looks like a transit, I would do one of two things. I would check to see if that system has a planet at all, as it should. And then secondly, if the Transit Ephemeris Service can give me a transit time window that lines up with the light curve. And this is essentially how this goes. So here you are at the Transit Ephemeris Service. You can do multiple targets. You can make a list of target names yourselves. You can also put in a single target, and we'll be doing that today using the same one. Let's say TOI-216.02. And then it will look around for sources that will get the ephemerides of the same one that you need. So here we have multiple sources, and to simply select one, you just double click or click on whichever one you're using, and it will autofill all the transit information that it needs to get your transit windows. Over here, you can do observer location. You can do space observatory or an Earth observatory. Let's say for this example, we can do Mauna Kea. And then finally in the observing window, the next event is especially helpful if you are in observing, but what I usually use is this, the window of the past dates, AKA I would put in the dates for that sector of time that this object would be observed in. So if we were to do, well, for this case, let's just do next event and then go ahead and hit predict events. And as you can see, there are no events because if I am correct, this one probably cannot be observed by Mauna Kea. So if we do independent of observer location instead, there is one event found. And it gives you essentially when the next transit would occur. In this case, it will be July 5th at 7:55 in the, well, that's the event midpoint, in July 5th. Sometimes they also include a start and end calendar if you choose a specific observatory to observe from. But this is a really great tool if you are double checking, looking for anomalies in pre-existing data. Multiple new planets have been found via this method. And that is exactly what I was aiming to do through that research. If you recall, there was a news story, I believe 2 years ago, about a 17-year-old NASA intern who did exactly this, and he found a new planet. Although the details of that story are up for debate. So that is a very general overview of the NASA Exoplanet Archive and what you're able to do with it. The amount of tools and the amount of data available in this site are, quite frankly, way too extensive to be covered in today. So to end this, I'm going to go over the tutorial that was created by our own Joey Murphy here, to help you kind of visualize how exactly to take data and how to use it in Python. So in this notebook, which is available on GitHub, I believe, or otherwise, it is essentially going to tell you how to do a mass radius relationship from the Exoplanet Archive for Kepler and how to visualize it. And then on your own, your job will to create a period versus radius relationship, as well as to plot any two parameters you want. Be sure to label your axes with units. So in this first one, very basic, we import our OS, pandas for data management, NumPy for math, matplotlib in order to graph, as well as matplotlib inline to essentially put our graphs to the side. This, in short, makes it run very nice. It makes it look very nice. So I'm going ahead and run that, make sure that that is all taken care of. And then for here, it is going to take in data. This file should be available to you previously in the data file in week 3. So it's going to load that in. It is essentially looking for a folder named data and then a CSV file called confirmed example. That name and that formatting is very important. Do not change the names of these files. So it's going to read in the CSV, and this is essentially what it pulls up. It gives us all of this information about these targets, the way that they were discovered, their orbital periods, a lot about their orbital periods, their masses, and the like. So what are the dimensions of the data frame? This essentially tells you how many rows and columns there are. Pandas likes to keep things fast and clean. So while we asked pandas previously to show the maximum amount of columns right in here, it does not show all of the rows to make sure that it puts out what it thinks you need to see. So now we're going to make a quick mass radius diagram. Here for matplotlib, we will essentially plot from the file these two columns, the mass and the radius in Jupiter mass and radius, as well as some basic visual parameters. This dot here is meant to make small unconnected dots rather than lines. The alpha is meant for transparency so that we can see more of the dots, as well as a density check. Go ahead and run that. As you can see, it comes here. However, it is scooted off to the side. This is a problem usually when a lot of certain points are propagated into a small amount of space. To fix this, a very common way to do it is to simply introduce logarithmic axes. And this way they become more spread out and the relationship between these two parameters becomes a lot easier to comprehend. So here we can see that there's 762 different planets represented here. The mass is in Jupiter masses and the radius is in Jupiter radii. And there are two kind of main populations here. A large one is up in the center, no, upper right. It's very dense and it's very propagated. And this is actually at around 1 Jupiter mass or so. It is much, much harder, or at least there are less planets that we find here that are less than 1 Jupiter mass, but they are there. So here it will tell you how to download a sample of exoplanet, how to download the next file. You go into the Exoplanet archive, you go to confirmed planets, you will add the columns of mass and radius in units of Earth mass and Earth radius. And in order to get specifically Kepler planets, you can put in discovered by Kepler via the transit method. So we can go ahead and I can show you how to set that up. Go on over to data, planetary systems. Let it log in. Okay. So as I mentioned before, you will want the transit method. And then when you get to Discovery Facility, if you click this little question mark tab, it will show you a lot of really useful commands that you can put in here. So if you want a string match, you simply just have to type in Kepler. And if you want to exclude targets from Kepler, i.e. if you are looking for transiting planets, but maybe with the TESS satellite or others like it, Kepler is responsible for a lot of transiting planets. So if you don't want Kepler planets, you can simply put not like, and then what you want to exclude. So here is the resulting large set. And in order to select which ones you want, you simply put select columns, and then you select your columns from the drop-down menu here. To make it easier, you can simply hit quit clear all, and then you are able to select without having to unselect what is already here. So after you download all of that with this, with these directions, and then save it into your data file to make sure that your computer can find it again, that OS can find it, go ahead and load it in. It will give you a size. That's how you know that it works. Load in the new data set. And this is what you should end up with. So then we're going to make a histogram to see the number of planets versus Earth radius.
Go ahead and wrap up in the next minute or so, Emily. We can leave the rest for exercise for the student if you don't get to everything.
So long story short, NASA Exoplanet Archive is a great portal for getting large amounts of information about confirmed systems. You could do anything from manipulate the data that is already in there once you have downloaded it, or specifically filter out what you need for smaller population studies. Your homework is also within this same Jupyter notebook, so please look for it there. And thank you so much for listening.
Emily, thank you so much. That was amazing. People are gonna have a lot of fun exploring the Exoplanet archive, like a lot of us get to do every single day as astronomy researchers. Thank you so much again. We're gonna transition now. While Chatan is getting this set up, I'll just make two quick announcements. Number one, I posted the attendance link to the Google form in the chat. You can go ahead and register yourself there as attended. Secondly, next week, and I'll send an email about this as well, is a holiday. And so we'll have the live version of the class on Tuesday, 5 p.m. Pacific, rather than Monday, 5 p.m. Pacific. Same Zoom channel. All right, Chatan, are you ready? All right, take it away.
Yep. So hi guys, thank you Emily for the amazing tutorial. So let's go on ahead, and I'll be talking about the Gaia archive and the Gaia tutorial. So before we move ahead, I'll just get full to make sure that everything is up to date from the website, and then I'll open the Jupyter notebook. And we are in week 3 Gaia tutorial. So you have this assignment right now, and the tutorial is also in the same notebook so that it's easier for you to navigate. So let's get ahead into it. So what is exactly Gaia? So Gaia is basically a satellite or a telescope by ESA, that is European Space Agency. Um, and it is primarily to measure the astrometric data for the Milky Way stars. So the astrometric data means we need to calculate the positions, distances, and motions of the stars and other solar system and other Milky Way objects. But it also like captures the spectroscopic data. So that is a measurement of spectra or different wavelengths of the lights that we are observing from the stars. And it also observes the photometric data. So that is the the luminosities and the lights of the stars that we are getting. And it's like a successor to the Hipparcos mission that was also launched by ESA in 2013. And its like major goal is to catalog all the stars in the Milky Way galaxy. And it also catalogs some other objects such as quasars in the distant galaxies. And if you have seen the video that Howard shared on the email, so these quasars are also used to reference its position and make it stable at one position. It is placed at the second Lagrangian point, which is it's a point in space where the gravitational pull due to the Earth and the Sun cancels out, so that it has zero gravity. And it gives us data in like micro arc second precision. So to get that into perspective, 1 micro arc second is something like a hair strand as seen from across the Earth, or a thumb that is on the moon and as seen from the Earth. So it is very precise in its measurements. And then Gaia provides us this data, and the main data points in Gaia databases is the right ascension, declination. So these two make up the global coordinate system. So these are just like latitude and longitude that we use on Earth. And you can read more about them over here. I put in a link. And it also provides us parallax, which is just like to calculate the distance. We calculate a parallax angle, which is just a difference in the position of an object as compared to a background when seen from two observation points. So whenever you hold a pencil in front of you and close one of your eyes, the same effect is called parallax. Then we have the radial velocity, which is the velocity of the star away from us or towards us in the radial direction, and the proper motion. So that are the transverse motions or the motions in the plane of the sky. So these are in RA and deck again. So proper motion RA and proper motion deck. And Gaia releases this data to openly to public in form of data releases. So we have currently 2 data releases. So one is DR1 and DR2. And we also have an early data release 3, EDR3, which has some enhancements over DR2. But we'll need some data from DR2 that in this tutorial. So you can also go ahead and try and see what's the difference between EDR3 on yourself. So and these data releases are present on the Gaia archive. So Gaia archive is just a site which hosts these data releases, and it also presents us a nice way to search and query this data so that we can use it for our research. So let's go on ahead and we'll look at the Gaia data archive, and we'll perform a basic search. So for that, we'll find 500. So first 500 stars that are present in the database for the Messier 5 object. So Messier 5 is a globular cluster in the constellation of Serpens. And we'll look at the sky at a 3 arc minute radius. So if we see a circle that makes a 3 arc minute radius, that is of a region of the sky that we want to look at so that we can get enough stars. And let's go on ahead and see what it looks like. So this is Gaia archive. And if you can see on top, we have a search tab here. So if you click on this, it gives us a nice little form so that we can fill out our details for what we want the data for exactly. So we want the data for Messier 5 object. So I'll type in Messier 5, and it resolves this name using some other databases that are Simbad, Net, and Vizier. So right now it resolved the name. That means the data is present for this object. And we need to look at a 3 arc minute radius. So I'll just put radius as 3, and from the drop down, I'll select arc minute. I can also select degrees or arc seconds. So I'll just go on ahead with something feasible for this point. And we'll search in a circle of this radius. And since we are using DR2, we'll just select from DR2 Gaia source. So Gaia source is the main table that contains all the source information. And here we have the maximum number of results that we want to fetch. So we'll set it to 500, that is the default. And we'll submit the query to see like what the results are like. So we have the results like queried very quickly, right? So we have 500 stars data, and currently it's just showing 20. And we can also download this data. And again, as you can see, there's a source ID that corresponds to a unique identifier to each star that is cataloged in Gaia Archive. Then we have the RA declination. So, and the corresponding errors. And then we have the parallax. So as you can see, there are some null parallaxes over here. So that means that we do not yet have the parallax measurements for these stars. And we have some other columns as well. So let's see how we can download this. So for that, we'll just go on ahead and use the same format that Emily used, the CSV, which are the comma separated values, since it's like very easy to use and easier to read using pandas. So we'll go ahead and do this to CSV, and we'll download the results. So I've already downloaded these results and I have loaded them in the tutorial. So for that, I'll just like, first of all, I have imported all the libraries. So we have NumPy, Pandas, Matplotlib, and the magic command Matplotlib inline, the same as we always do. And if we see, I have saved this data as m5.csv in the data folder. So this is right now not present in the repository. So I'll request you all to go on ahead and try doing this on your own so that you can get familiar with the archive. And we first see like what are the number of rows and columns, and see the top 5 rows of the data that we got. So we have 500 rows and 14 columns, and this is the same data that we saw on the archive. So every null column is presented as an NaN, that is not a number. And if we try to plot this thing, so I've just taken a figure from matplotlib and plotted a scatter plot using the RA and declination values. So just the position of the stars in the sky. And if you see, we have all these stars and they are positioned randomly. So like, these are the top 500 stars that are present in the database, and they can be arranged randomly or ordered randomly in the database. And I have also plotted this central point, which is the central point for the Messier 5 cluster. You can find this using here. So we have this show query in ADQL form, and we'll go about what is ADQL later in the tutorial. So you can see there is some code type of thing written over here that is a query. And you can find the central coordinates of this object from here. So I've just put in these two values, RA and dec, in the tutorial. So this is how we fetch the data from like the Gaia archive. But what if we want to include some more conditions and get some more complex data? So for that, we'll again use the basic search functionality that we just used. But right now we'll be searching for Messier 92. That is again another globular cluster in Hercules constellation. And we'll now put a 1 degree search and put in some extra conditions. So for that, we'll say that we want to look at stars which have a parallax greater than 5. And we'll say that we need to see at stars which has parallax over error greater than equal to 20. So that means the parallax divided by the parallax error. So that means the parallax measurements are like very correct. And then we'll also see what all display columns that we can select. So we'll select some more columns, typically the proper motions this time. So let's go on ahead and try again the same thing. So I'll need Messier 92, and it is resolving the name. It did resolve the name. We need to search in 1 degree of radius because we are putting in some extra conditions and we want to get a significant number of stars to plot. And here in this tab, you can see we can add extra conditions. So let's add a condition. The first drop down is just all the columns that are present in the data. So we'll select the ones that we want. So we want to say that the parallax is greater than equal to, so I've selected greater than equal to over here and say 5. And I need another condition over here, that is the parallax over here is greater than equal to 20. So I'll just put on that, and I want that both of these conditions should be true. So I put filter is equals to if all conditions are true. If I wanted any one of these conditions to be true, I can just go on ahead and say if any condition is true. So this is the and the or functionality that you might have seen in Python. And then we have the display column. So you can select any number of columns that you want, and you can experiment with this again. But for now, I'll be putting in PM array, that is proper motion array and proper motion index. And the maximum number of results is again 500, submit query. Let's searching. And yeah, we have 160 stars that corresponds to both of those two conditions and are in the Messier 92 object. And we also have the PM array and PM deck. So one thing to note are the units, and you can see all the units that you have here, so that you can convert these units into your own set of usable notations. So let's say that you can want to convert parallax into distance. Please note that the parallaxes in Gaia are in milli-arc seconds as compared to arc seconds. So you'll need to divide it by 1,000 and so on. And I have again downloaded this data as a CSV table, and I have already downloaded it on my system. So I'll just go on ahead and read that CSV. So I have put it as m92.csv, and I see what are the number of rows and columns. So I get 160 and 22. And then I again plot the RA index, and we can see how the whole cluster is organized for all the stars that have parallax greater than 5 and parallax over error greater than 20. And I have also plotted in some histograms for the proper motions. So you can experiment with what you want to do with the columns, and if you want to select other columns, etc. And now moving on ahead with the ADQL. So what is ADQL and why do we need to use it? So right now we are just putting in some extra conditions that are limited by these operations greater than equal to, less than equal to, and not equal to. But what if we want to do some more complex operations? Let's say I want to match two of these tables, let's say EDR3 and DR2, and want some particular data from that. So for that, we use ADQL, which is a language that is very similar to SQL, if you are aware of. So it's structured query language. And these languages are used to basically fetch data from these relational tables, that are tables which have columns of data and rows of data and are related to each other. So let's say there are two tables that are related to each other with a reference column. That would be the source ID over here. And these queries are structured in a particular format. So these are just like commands that we saw in Python or Unix, but they are a bit different in the way that they need certain things or certain parts. And these are the parts. So the first part is the select part, which tells us which columns we want to fetch. So let's say I want to fetch 5 columns, I'll put in the names of the columns. If I want to select all the columns, I'll just put in a star. And if I want to also select a set number of rows, so let's say top 100 or top 500 rows, I can put it like select top 500 and then the column names. Then the next part is the from part, which tells us which table we want to fetch the data from. So here you can see an example. So from Gaia dr2.gaia source. So here Gaia source, sorry. Yeah, so Gaia source is the table here, and Gaia dr2 here is the schema or the database name. So schema is just another way to say that we are going into the database. So we need from dr2 Gaia source, these columns are needed. Then these two are the optional forms or optional parts. The where part tells us the conditions that we want. So in the previous example we saw, so we can say parallax greater than equal to 5 and a parallax over error greater than equal to 20. This and here tells that both these conditions need to be true. And then there is an order by part. So we can order the data accordingly how we want from a set of columns. So let's say I want to order the data according to the parallaxes so that I can get the closest or the farthest some 100 or top 500 stars. So a whole query looks like this. Select a number of columns and from table where some conditions are met and order the data by some particular columns again. So let's try on and write a query, simple query. And this would be to fetch the closest 100 stars to Earth. So for that, we'll just write select top 100. So since we need the top 100 results, again, we are only fetching the closest stars. So that means we'll need to order them by something, and we'll see it in the end of this query. Then I am putting in the column names that I want to fetch. So these are the column names. First, I have written the table name and then dot with a column name. So you can omit this table name if you are only working with one table, but this becomes very useful when you are working with multiple tables, so as to remove the ambiguity between different columns of different tables that might have same names. So I want source ID, RA deck, RA error, and parallax error. And I need to fetch this from Gaia DR to Gaia source. So this is the from part. Then there is this where part. So I put in that parallax should be greater than equal to 0, so as to avoid the null rows that we found in parallax earlier. And then I'll order this data by parallax in descending format. So parallax is just 1 over distance. So we are ordering it by parallax descending. That means we are ordering it by the distance ascending. So we have the top 100 stars, which are closest to us because we are ordering the data using this parallax. So this whole query looks like this. Select top 100 and the columns and from and where and the order by statement. So I'll just copy this statement and go on ahead to the archive. Here we have this ADQL tab, and you can delete this already existing query over here, put in your own query. And here you can see we have this submit query form. If you submit this query, it assigns a job to it on the server, and this data is fetched for us. You have some other buttons over here, so you can look at the data using this button, display top 2000 results. So this gives us the 100 rows that we fetched. And if you can see, like, we have the only the columns that we put in the query, and we do not have any null parallaxes because we already put in that condition. Going back to the ADQL tab, so I'll just download this data and format it as CSV, and I can download it using this button. Or again, I can also download it from here like we did earlier. So I have downloaded this. Yeah.
This is going great. Go ahead and finish up in the next minute or so, please.
Yeah, sure. So we have the closest 100 stars data, and I've just printed it to see if everything is correct. You can experiment with whatever you want with this closest 100 stars data. So this is the tutorial part. Now, what is your assignment is basically to go through what ADQL is in more detail. You can check out this website that I put. So here you can read some queries and this web page. So this web page is pretty long. I'll only ask you to read till the example queries. There is no need to read those example queries. If you are interested, you can always go ahead and read more. And there are these 10 or so slides in this PowerPoint that you can read. And what we have to do in the assignment is we'll plot an HR diagram. That is a color magnitude diagram that you might have already seen a lot of places. So we'll fetch in 10,000 stars. So just like we fetched the top 100 stars, and these will be the closest stars. We'll be fetching these columns. So the first and second column will be used for the HR diagram, which is the BPRP color, which is the blue photometer and red photometer color, and then the absolute G band photometric magnitude. There are hints, please feel free to use them. You'll be needing these. And here we can, you'll have to plot this diagram, and then there are some bonus assignments. So there is this paper, you can compare your figures with this paper only. You do not need to read through the whole paper. And then there is one section in this paper, and try to reproduce their plot. And then there is another challenge or bonus assignment that if you have time, you can go ahead with this. So we plotted a 3D plot in the week one, that if you remember. So you can use this 10,000 stars data and try plotting it using the week one tutorial itself. So you have the code already. And this is just an annexure. So if you want to do the same thing using Python, you can put in a query using the Python. So this can launch a job itself from Python itself. So that would be all. Thank you so much. Thank you, Howard.
Thanks, Shaitan. That was great. And thank you for all the questions that came through on the chat. That was great. We're going to get to those best we can. Feel free to follow up your questions on Piazza. So we'll transition now to Isaac, who's going to discuss the TOI-700 paper. And be sure to stay tuned after that for 2 more mentor profiles. Jack and Corey will be giving those today. So Isaac, go ahead and take it away.
Hello, everyone. Howard, if you don't mind letting me start the video. I can share, but I'm not sure you can see my video yet. Cool. Does that work for everyone?
Oh, you can see your screen. Yep.
Okay, awesome. Hey, everyone, I'm Isaac again. I'll be presenting a paper on the TOI-700 system. So you can find this paper on the GitHub link. And then I'm also going to post some discussion questions. And please try to discuss the paper on Piazza just to get a sense of it. It helps so much to go through these papers with everyone else and to get a sense of like what you know, what you don't, and insights that you could draw from it. One of the things about astronomy papers and academic papers in general is just how dense they are. Like this is not like a nonfiction book even. Like I find I'll read like a page of an astronomy paper and then like take a 10-minute break. They can be really, really dense, especially in parts of very niche papers where they assume that you know a whole bunch of information that you might not. Like they'll go into some topic about how to like separate stellar signals and stuff like that, and assume that the reader is very experienced because most of their readers are. But just when you're reading astronomy papers in general, and a lot of this one, don't feel bad at all if there are big sections that you read a sentence or two and you're like, well, what are they talking about? So today, without further ado, I'm going to be presenting this paper on the first habitable Earth-sized planet from TESS, validation from the TOI-700 system. So the way that I like to start
your video, Isaac, if you'd like to.
Oh, thank you. Awesome. Cool. I know that sometimes it's easier to present. Cool. Yeah. So this paper is about observing the planets in this system. You can see this is like a kind of broad type of astronomy paper. Some are theoretical, some are observational, some are computational. This one you'll see is just like we found these planets. So they do a whole lot of background information stuff and a whole lot of methods. But one of the main takeaways is just like we got some planets. And these are really helpful whenever you're trying to do any other type of paper and you want to look back and find like, what is the mass of the planet, stuff like that. So the thing that I think if you want to get a lot from the paper that you should start with is just going over the abstract really, really carefully, because the abstract is kind of what the authors want to convey most of all. And if it's a well-written paper like this one is, the abstract is like both really dense, but also pretty readable, because they try to make sure that you can get the main points without being lost in like any of the methods of like Bayesian retrievals. So you can see here just starting, they present the discovery and the validation of the 3-planet system orbiting the M2 star TOI-700. So just as a reminder, star types are based on like the first letter. So like it goes, I remember with the mnemonic, oh, be a very fine giraffe, kiss me. And that letter corresponds to the type of the host star. So this is an M2 dwarf star. The 2 is just like a subcategory of the M star. And it has 3 planets that they're presenting that they found within this paper. And they found it with TESS. And they're presenting these planets, describing the system a little bit. And then they talk a little bit towards the end about how the system might have formed, as well as the possible follow-up with the James Webb Space Telescope, which should be launching very soon. I'm not going to go over a ton of the introduction and the methods that much, just because they're pretty dense. This paper does have beautiful figures, so please spend some time to go through. This shows how TESS observes the sky and like the type of image that you'd get from TESS. A lot of their methods are just pretty standard ones about how we observe planets. So there's a whole lot of background that's now like kind of assumed to be not really common knowledge, but like how these planets are found. So please go through, look at the methods, but they're pretty dense. One thing I do want to point out is this table of stellar parameters. This is pretty useful if you're just browsing through and you want to find the information about the star, so TOI-700. This is the right ascension and declination within the sky at the time of the observation. The spectral type is M2V, the effective temperature, the mass, radius, and luminosity. These are all in units of like our sun. So this means it's a little bit less than half of the mass of our sun, a little bit less than half the radius, but way less than half of the luminosity. That's like 2% the luminosity of our sun. Some other stuff about density, rotation period. One thing that I do want to point out is that they are really uncertain about the age of the star. M dwarfs are very long-lived. Generally, the smaller the star, the less massive it is, the longer the lifetime. So all they can say here is that the age is greater than 1.5 gigayears, so greater than 1.5 billion years. But there's a huge uncertainty. Like we wouldn't be able to say this star is 10 billion years old or something like that. Cool. So going through a little bit more, that was all about the host star. They have similar stuff with the planets. You can see these the 3 planets that they find, B, C, and D. Generally, we'll name planets like B will be the most interior planet. One thing I want to point out is you can see this is the temperature of the planet right here. These are all very, very tightly orbiting planets. Like these are 1300 Kelvin approximately, which is very hot, much hotter than Earth. Generally, right now, we're finding planets that orbit their host stars very closely because those planets are easier to find. The general move in observational astronomy is trying to find more Earth-like planets. But the problem is the further away a planet is from the host star, generally the harder it is to find. There's some wiggle room with that with newer types of observations, but just like the first planets that we found were hot Jupiters, which are huge and they're orbiting their host star very closely. So they're very easy to find. You can see here's like the period of the planet, the ratio of the planet to the star, the radius. So the first one is about 1 times the radius of Earth, and then a much bigger one, 2.63, and then another one that's about the radius of the Earth. Cool. Just scrolling through a little bit more. This was a very, very detailed paper. They go through a ton about their methods, which I think is great because it means that when you're trying to like read it, if you really care, you can like go through and be very sure of what they did. The last thing that I want to point out is that at the end, when they go over the discussion, they talk a lot about how these planets inform our understanding of general planet systems. So you can see here, I really like this diagram that they have of the system. I think these diagrams are great and kind of underutilized in scientific papers, just because I think they convey a lot of really basic information, even though they're not like a fancy graph with like Bayesian statistics. But I think to me, I look at this and I like have a very intuitive sense of what the system looks like. And they talk a lot about one of the ongoing questions in exoplanet astronomy is how exoplanets lose their envelopes based on how irradiated they are by the host star. So one big theory is that extreme ultraviolet radiation from a host star can blow away the initial primordial envelope that these exoplanets have. And this system is really interesting because that one Earth radius planet and followed by a much bigger planet, followed by a much smaller radius planet, informs our understanding about how these exoplanets can lose their atmospheres. So by getting a whole system of planets and like a whole catalog and understanding the distribution masses and radii, you can kind of make much more informed guesses about how these exoplanets might lose their atmospheres. Cool. So that's everything I wanted to present on this paper. I definitely recommend reading it. I think it's really useful and a great paper overall.
Thanks, Isaac. That was great. And we have all week for everyone to follow up on Piazza. If people feel like having more of a discussion, we can all chime in and learn something new about the paper. There's a lot of fun systems like this. This is just one that we picked out in order to give people an introduction to TESS and habitable planets and planet detections and characterizations and things like that. So be sure to search around if you have other types of planets that you're interested in. Thanks again, Isaac. All right, I think we'll go to our mentor profiles now. So Jack, would you like to go first?
It says I'm unable to start my video.
Oh, that's my fault. Hang on one sec. Classic Zoom. Try now. Oh, almost. Try now.
All right. Hi, everyone. So I'm Jack Lubin. I'm a fourth year grad student at UC Irvine currently. And I guess so I'm just telling you a little about who I am and kind of my path to grad school. I have a little bit of an interesting path that I'll get to in a second, or that we'll get into. But starting with the beginning of my path, I mean, I was always interested in the space race, and I watched a lot of documentaries and movies about the beginnings of the space race, and learning how to build rockets, and then eventually the actual the moon race itself. And that always really fascinated me. I always wanted to kind of be a part of something like that. So those documentaries and movies, I mean, those really got me more into physics, which then got me into astronomy. So I've always been really fascinated with these topics. I think that's somewhat of a common thread through a lot of astronomers, sense of, wonder and discovery, looking at the night sky and stuff like that. That definitely describes me as well. But I remember I didn't actually take a physics class until my junior year in high school. So that might be relatively late or so. But I had a really great teacher. He was like really supportive and inspiring. He tried to make the material fun, and it really turned out to be a lot of fun. And that's when I really started realizing that physics and then later astronomy could be something that I could do. It would always seemed kind of out of reach as something that was, these talking heads in a documentary or in a museum or something like that. These people, they seem kind of unattainable, but then to take a course where the material was like really brought down to earth in some sense, made me feel like, oh yeah, maybe I can do this too. And I remember I went to undergraduate, I went to college, and my freshman year I took an astronomy class, and that's when I really said, okay, this is what I want to do. But then I also realized pretty quickly taking that class that the school that I was at, they didn't really have much of an astronomy program. They really only had one more astro class. They didn't have a whole lot of physics classes. It just turned out to not be the right school for what I wanted to study. And so I made a really difficult decision, and I transferred. I transferred to a new undergraduate institution. And so I specifically looked at schools that had, strong physics and astronomy programs. And I look back on that as it was a really tough decision at the time. I mean, I had a lot of friends from this first school, but it turned out to be the right thing. And I think I would not be where I am today without making that tough decision. And so that's maybe like one thing that I think is important to take to heart, is that just because you're at some institution or school, whatever, doesn't mean it's right, or it doesn't mean it's right for you. And there's no shame in looking elsewhere for if you want to do something, and that institution can't support you in the way that you want. But I remember I got to the new school. I took a whole bunch of physics and astro classes. I was really excited. My course counselor told me I had to take a computer science class, and I didn't really want to do that because I wasn't interested in computer science and coding. But I took the class anyway. I hated it. And then it turned out to be the best thing I ever did, because then when I went to a professor who I wanted to do research with, the first thing he said to me was, okay, can you code? And I said, well, actually, I'm not very good at it, but I can. But that's how I got my first taste into research. I literally just, I asked. I had a professor that I did fairly well in his class, and I went up to him after and said, I want to do some research. And I think professors really like that. When you kind of show that kind of initiative and desire to do more outside of a classroom. And it's definitely scary. It's definitely scary going up to someone and saying, can I work with you? But I think it works out almost all the time, at least within reason. But yeah, I did a whole undergraduate honors thesis with this professor. I worked with him over a summer. That's when I really dove into astronomy and research, and I really, really enjoyed it. But I also knew that I felt like there was something missing, and I knew that I didn't feel like I was quite ready for graduate school. And this is where my path kind of becomes maybe non-traditional. Is I actually I graduated from my undergrad, and then I took a job actually at a bank. So I didn't go to grad school. I didn't even apply, didn't even send an application. And I worked for this bank doing software development for them for a bit. And because I wanted to know, what else is out there. I've been a student my whole life, 15, 16 years of education. And it's like, what else is out there? So I wanted to go into the real world to some extent. And I'm really glad I did, because I ended up hating it. I ended up really, really hating that job. I did not like what I did. I was not inspired by it, not passionate about it. Woke up every morning dreading going in. And I said to myself, it's time to go back to the things I really enjoy. And that was astronomy research. So I quit the job, fired off some applications to schools, got in, and I don't look back. I mean, it was the best decision I ever made after, I guess, transferring undergrad institutions. And I think it really took me that extra, I was working for this bank for about 18 months. It took me those 18 months to really figure out that, I wanted to do astronomy research. It's the only thing I want to do. And there was a way to do it. And the way was, kind of take a little leap, quit the job, and throw off some applications. So that's kind of my non-traditional path. And I wanted to highlight it because I had a lot of people tell me that if I didn't go from undergraduate directly to graduate school, if I didn't do that, then I would never get into graduate school. I had a lot of people tell me that. And it definitely was in the back of my mind the whole time, but I also was pretty determined. I said, I'm going to give, the real world again, I'm going to give it a shot. And if not, I'll try to go back. And I feel very fortunate that it did work for me, but I'm also sure it could work for you. It's not something, you don't have to feel like just because you're not going directly from undergrad to graduate school doesn't mean that door is closed at all. In fact, it might even make you a more attractive applicant or a better graduate student later. I feel like the things I learned working that job, not necessarily the technical skills, but just the way to work and the way to work with people on projects, I think that definitely helped me as a graduate student. So that's kind of my story. I think that's all I got here. Thanks for letting me share.
Jack, thank you. We'll take a minute for everyone, let that sink in a little bit before we transfer to Corey. Might be some of you out there who can take a page out of Jack's book, take a leap, make a big decision that you think is right for you, and change your course, change your path. Thanks, Jack. I really appreciate that. And we'll hand off to Corey now.
Okay, hey everyone. Thanks, Jack, for sharing that. That was interesting. My name's Corey Beard. So I know Jack pretty well, actually, because we're both students at UC Irvine together for the same professor. So we work together closely, but it's always cool to hear some stuff about Jack's background. And even I learned something, listen to that. So thanks for that. So now I'm going to go into my background. Mine is, at least compared to some astronomers here. I mean, so Jack said his was untraditional because he, of course, left school and then came back. Mine is a little less traditional in a different way. So I'll get into that in just a second. But also with him and a lot of the other mentors like to say, my story starts just being a kind of a young kid, starry-eyed kid who just loved space and I remember at the time I loved black holes and dark matter, not even knowing anything about what these things are, but loving just the concept and what they kind of created in my mind. And actually I have a little picture to share if I can, and I think, am I able to share my screen? Let's see. Yeah, okay, cool, I can. So basically, I'll do that in just a second, but one of the things that really got me into it, it's not like the first thing that got me into it, but me and my brother got a Christmas present, which is a giant, I think it's a coffee table, it's for a coffee table, a giant book called Astronomica. I don't know if anybody's ever heard of it, but it was a giant book that really got me into it. So I don't have a picture from when I was a kid, but my brother has it. So I took a picture over the weekend to show everyone how, I don't know if you all can see this, but it's a pretty enormous book. And it's got these cool full page kind of like fold outs of like, star clusters and stuff that just look awesome. I think most of them are taken from the Hubble telescope and that sort of thing. But yeah, that's one of the things that got me really into astronomy, and I really, really liked it. Actually, similarly to Jack as well, I took my first physics class junior year of high school, so maybe it's not so late. But at the time, that was my first introduction to physics, not just astronomy. And I liked it, but I wasn't in love with it. But as kind of a lot of people around that age are, there are probably some high schoolers and early college people in the audience here, but a lot of us don't really know what we want to do. So I was like, you know what, I'll go for it. I'll do physics. I'll do something with physics. That's what I told myself. So when I went to school, and I went to the University of California, Los Angeles, so UCLA, as it's more commonly called. That's where I went to undergrad, which has a pretty strong astronomy program, especially since one of the faculty just won the Nobel Prize recently, which was great. So I went there, but I actually didn't jump into astronomy off the bat, or actually really at all while I was there. And this is where my story is maybe a little strange. So I kind of went along, kind of following the classic series of classes and stuff like that. My first research experience wasn't until my junior year there. I'm later than some people, earlier than others, but mine was non-traditional. I studied abroad in Japan, and that's where I did my first research. I did some plasma physics at a lab in Osaka, Japan, which was a pretty cool time. Really, different and the same in the United States. And it was my first research experience, so I didn't have anything to compare it to. But basically, while I was there, I just did my best to try and learn what the heck was going on. I'm not going to claim I did any sort of real scientific research. That is to say, I didn't contribute to proper plasma physics, but I did learn the basics of some research, the basics of coding, that sort of thing while I was there. When I got back to UCLA, I was actually kind of near graduating. So from there, I started doing research, not at UCLA actually, but UC Irvine, which is where I'm at now. I started working in a completely different subfield of physics, still not astronomy. I started doing particle physics, working for a professor here at Irvine named Daniel Whiteson. And I actually really enjoyed particle physics for a really, really long time. My interest in astronomy was still strong at this point in time, but I just told myself that particle physics is what I wanted to do. And that's what I did for a while. I took a year off between my undergrad and grad school, but I knew I wanted to go to grad school. I applied for particle physics, and that's what I got in for, and that's what I came in doing. But a little before I actually started at UC Irvine, some personal stuff happened in my life that made me kind of lose interest in like everything I was doing. I couldn't stand to do particle physics. But what I found was that I was still really interested in anything astronomy related, even though I was not in the best place. And I took that as a sign that meant that I probably should be doing something other than particle physics, and maybe astronomy was the right path for me. And I have to say, it was one of the best decisions I made. I switched into astronomy. I had never even heard of an exoplanet at that point in time, but I kind of looked around for what interested me, and sure enough, exoplanets were the one. And no looking back, that was a really great decision. I couldn't be happier where I'm at right now at UC Irvine, doing lots of really fun stuff here. And so, wrapping up a little bit, mine is, my story is just one where, even if astronomy, I think most of you are probably interested in astronomy, which is why you're in this particular thing. But even if something other than astronomy is what your final goal is, don't feel also constrained to sticking with what you've been studying in undergrad. I didn't take a single astronomy class in my undergrad, and yet here I am doing astronomy research in grad school. It can be done. So anyways, that's kind of just my story and how I got where I'm at. And yeah, thanks for listening. Hopefully you learned something, or feel like you're inspired or encouraged by something that I shared.
Corey, thank you very much for that. Let that sink in before I wrap everything up here. So that was really great. Thank you, Jack. Thank you, Corey. And thank you, Shaitan. Thank you, Emily. Thank you, Isaac, for leading the discussions today. from those last profiles, I think that you can see that it takes all kinds in astronomy, and anyone can be a part of it. You just gotta make the decisions that will lead you that way. And helps if you love it, helps if you are inspired by it and want to do it every day. Please keep your discussions going on Piazza. Have a look at the tutorials from Exoplanet Archive and Gaia and work on those assignments. If you have questions, let's talk about it. Let's get you guys some experience with these things, these tools that we use every day. It's a lot of fun. And tune in next week. Again, Tuesday, 5 p.m. Pacific, 1 day later than this week. I'll send a reminder and some links and whatnot. Until then, take care, everybody. Thank you.